Everything looks like it's up and running as it should. Just move the mic there a little bit. Right. So I'm back again. I haven't forgotten you. So last time I streamed was day 8. As you can see, I've also been cheating a little bit and doing part 2 of day 8 off camera. I don't think we have time to go into it today, but I will go through what happened here at some point. But yeah, I'm not going to do 9 or 10 either today. I think we're going to focus on day 11, and then maybe we'll come back and do these at some later point. But for now, we're just going to skip straight ahead to day 11. Right. Yeah, everything still up and running. So yeah, day 11. I haven't done 9 or 10, but I haven't looked at day 11 yet. Right, day 11, cosmic expansion. Oh wow. Ooh, now we're missing story. I don't like that. Oh well. You continue following signs for hot springs, and eventually come across an observatory. The elf within turns out to be a researcher studying cosmic expansion using the giant telescope here. He doesn't know anything about the missing machine parts, so apparently there are some missing machine parts. Oh yeah, we were looking for those on day 8 as well. He's only visiting for this research project. However, he confirms that the hot springs are the next closest area likely to have people. He'll even take you straight there once he's done with today's observation analysis. Maybe you can help him with the analysis to speed things up. Of course we can. The researcher has collected a bunch of data and compiled the data into a single giant image, which is our puzzle input. The image includes empty space as dots and galaxies as octorps or hashtags or hashbangs or whatever you want to call this symbol. For example, so here just a bunch of dots with some pound symbols or octorps or whatever. The researcher is trying to figure out the sum of the length of the shortest path between every pair of galaxies. So the shortest path between every pair of galaxies? Okay. However, there's a catch. The universe expanded in the time it took the light from those galaxies to reach the observatory. Due to something involving gravitational effects, only some space expands. In fact, the result is that any rows or columns that contain no galaxies should all actually be twice as big. For example, this doesn't contain any galaxies, so it should be twice the size, I guess. In the above examples, 3 columns and 2 rows contain no galaxies. These rows and columns need to be twice as big. The result of cosmic expansion therefore looks like this. Equipped with this expanded universe, the shortest path between every pair of galaxies can be found. It can help to assign every galaxy a unique number. 1, 2, 3, 4, 5, 6, 7, 8, and 9. In these 9 galaxies, there are 36 pairs. Wait, how do they do pairs? Only count each pair once. Order within the pair doesn't matter. For each pair, find any shortest path between the 2 galaxies using only steps that move up, down, left, or right exactly one dot or pound at a time. The shortest path between two galaxies is allowed to pass through another galaxy. Right. For example, here is one of the shortest paths between galaxies 5 and 9. Down 1, over 1, down 1, over 1, down 1, over 1, down 1, over 1, down 1. Well, I guess it starts with a down 1 as well. This path has length 9 because it takes a minimum of 9 steps to get from galaxy 5 to galaxy 9. The 8 locations marked pound plus the step onto galaxy 9 itself. Oh, so this doesn't count as a step, apparently. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Here are some other example shortest path lengths. So 1 to 7, from this one to this one, 15, 3 to 6 is 17, and 8 to 9 is 5. In this example, after expanding the universe, the sum of shortest path between all 36 pairs of galaxies is 374. Expand the universe, then find the length of the shortest path between every pair of galaxies. What is the sum of these lengths? So I'm guessing that 36 is just every pair of every galaxy. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so there's 8 per... Oh. But order doesn't matter, so this one shouldn't be counted again. So yeah, I guess that's just... 36 is just the combinations of 9 things. Yeah, only count each pair once. Order within the pair doesn't matter. And the sample input looks like this. So to begin with, we have to do the expansion. Now, in the previous days, we've been either using npeg or we've been doing just sort of a line and parse directly kind of thing. Of course, when parsing lines, we could quite easily expand these, which are empty. But it's much harder to do columns when we're going line by line. We need to basically keep track of which columns don't have pounds in them, and then at the end look at all the columns without pounds and expand. Of course, we could do the actual expansion, create this in memory and do the actual expansion, or we could have sort of just a table of expansions, and when we're calculating the lengths, we could do the what's it called? We could do the sort of look into the skip table and see. So between this and this, it would see that, okay, between them I have this number, so I know that the length, or I know that this xy has to be one larger than it would have been. And same goes for this. So we have to add 1 to the x offset and 1 to the y offset for this pair of 1 to 5. So yeah, how big is the actual input? Right, so big-ish, but not terribly big. Yeah, so let's do our sample input first. Oop. That wasn't the whole thing. Right, sample input. Yeah, so with all the expansions, it would of course get bigger. So part 1. So what we could actually do, instead of storing this entire map, we can just store the XY positions of all of these and figure out which columns and rows are missing galaxies. So we can have galaxies be a sequence of tuples of XY. We can have well, I guess we could collect them in line. We could also collect them sort of afterwards, but let's collect them in line. Galaxies X is a set. Well, yeah, sure. It's a set of how long is this input? It's quite a long line, isn't it? I think it might be longer than come on. Let's see, that is, well, it's only 140 odd characters. So we can use a what? There we go. We can use a set of unsigned integer for this. And we're going to do the same for the y direction. There. And then we'll just say for each line, let's do a for x comma line in lines. That would actually be y in lines of the sample input. Then we do for x comma galaxy or empty space would be our tile, I guess, in this line. If the tile is a galaxy, then we say galaxies X include the X position, galaxies Y include the Y position, and add this galaxy to the list of galaxies. So I have done this a couple of times. Not sure if anyone has noticed. If you do this, this is now a call to add with a tuple or with two arguments, and this would fail. Oh, that failed for multiple reasons. We need to grab string utils for the lines iterator. I believe this apparently does not have an oh, maybe we didn't need that. Enumerate. Oh, that has to be in the... So new packages require the std prefix. Old ones don't, which is a bit annoying. So yeah, do this. So yeah, here we have an error, XY. We have a type mismatch. If I do this, we don't have a type mismatch because this is galaxies.add in command calling syntax, and this is a tuple. So this is a call to add with two arguments. This is a call to add with one tuple as the only argument. Might be a bit confusing. So yeah, now we basically have all our galaxies in the X and Y direction, and we have all of our galaxies listed here. So if you go ahead and compile and run part 1. We haven't gotten to part 2 yet. So we can see here that we have galaxies in 0, 1, none in 2, 3, 4, none in 5, 6, 7, none in 8, and 9. So those would be across here, this one, and this one. And then this one, of course, we have more, but we're missing 3 and we're missing 7. So we're missing 2 in that input. And of course, we have the coordinate of all of them. So the first one is found at x3, y0, which of course would be this one right here, starting from 0, 0. Right. So now, yeah. Now we basically need to figure out, so we need to go from all of these to all of these, which one in this, or what's the distance from this to this, from this to this, from this to this. And the way we're going to do this, so we're going to iterate over all of these, and for all of them, compared to all which are 1 ahead. So that means we'll compare this to this, and this, and this, and this, and this. This one, we're not going to compare it to this because we have already compared it to that. So we're only going to compare it to 1 ahead and forward. That makes sure that we don't have any duplicates. And of course, when going through this, we will then know that, or we can then figure out that, okay, between 3 and 7, in this direction, between 3 and 7, we are missing a 5. So we need to add 1 to the offset between these. Well, for this one, there's no offset. This is of course comparing this one to that one, but we have to offset this by 1. And for the distance, so this is not like a regular, this is not a regular distance of just like diagonal distance. So we need to figure out something there. I'm not quite sure. Well, we can do some for loop stuff there. So for galaxy and galaxies, and for we need the position because we're going to loop from the next one ahead. We're also not going to go all the way to the end because the last one we don't really have to compare against any other. So we're going to skip the last one. So if we now print out all the galaxies, we will see that sorry. We will see that the last one here is actually the second last one here. Because this is going to compare with this, and this one doesn't have anything else left to compare with. This is a bit slow in NIM. It's we are basically here taking galaxies, making a copy into a new sequence for the slice, which isn't the fastest thing in the world. I think it might do optimizations in for loops now, but I'm not 100% sure. In any case, if we need the speed up, we could always go from galaxies.low to galaxies.high -1. And then, well, I can show that. So we could do from galaxies.low or just from 0, because who doesn't start their sequences at 0, all the way to galaxies.high, but, well, not all the way. And then we can say that galaxy is at position I. So this would do the same thing, but we wouldn't copy this into a new slice. Great. So now we need to go for the second galaxy. So let's call this first and for second in first. So we start at our position +1, and we go to, in this case, galaxies.high. And let's call this first, and let's call this second. We can echo out the first. The word 2 and the second one. And we will see here that we now get a bunch of these. So comparing this one to that one, all of these to all of those, and then this one to this and forward, because we already know that we compared it to this one. If of course we set up a, well, let's just use a sum variable that we're gonna use for something else afterwards. We can do this, we can echo out the sum at the end. We should see that this should be 36, which is what the sample here said, all the 36 pairs. So that's good. Now we just need the distance. So we're going to test compare 5 and 9 is the one that we know the expected distance between. But we're just going to write this for all of them. And their indexes, or their index starts at 1. So we need to compare f plus 1 to s plus 1 to get the indexes that they expect. So if we want the, what was it, 5 to 9, that would be this one right here, which is the one we're sort of interested in. So now we need to figure out the offsets for the galaxies, or between them. So we need to get like we're moving x steps in this direction and y steps in this direction, or actually just like the absolute value of that. So let's get the sort of dx and dy. Start with dx. Dx is going to be the absolute value of second.x minus first.x. The order doesn't matter because we're doing absolutes or absolute values. Oops. Of course, this does not take into account any of the expansion. So from here, from 1 to 2 is a distance of, says it's a distance of 4 in the x direction only, looking at this. So from this to this would be a distance of 4. So 1, 2, 3, and 4. So that's correct. But of course, we have this expansion between them. So we should do the expansion there. And the way we can do that, so we have the position of this, we have the position of this, we have the positions of all the columns with galaxies in them. So we can take the range from this to this, or we can take the range from there to there, and turn that into a set, subtract the set with galaxies, then take the cardinality of that set. And I think for that, we are going to have to grab set utils and maybe specify that we're looking for the nim one. Because this has a toSet, which allows us to pass a range. It's great. So let's grab, we're just going to do this sort of after for now. But we're going to bake it in so we can keep this let here. So we have two sets. Oh, and we actually need to grab the package, as I said. So set utils for that. Oops. Two sets the smallest of second.x and first.x all the way to the largest of second x and first x. Oops, that should have been a comma. All the way to the largest. This is of course superfluous. There we go. And then minus, remember from looking at sets, minus between two sets is the I don't remember what it's called. Doesn't really matter. Are galaxies dot x. Oop, and let's just echo that. Oh, not dot x, galaxies x. Oh, of course. We need to turn these into unsigned integers to get those sets of the same kind or the same type. So now we can see that between 1 and 2, we have a set containing column 5, which is of course this column right here. And between 1 and 3, we have column 2. So between this and this, we have column 2. Between 1 and 2, 3, 4, 5, 6, we should have 2. So between 1 and 6, we have 2 galaxies. That's fine. So we can now just add on this count because they are going to count double. So they're already counted in here, and now we're going to count them again in our set. We're going to do the same on this line, but let's just do a let's do a search and replace for .x to .y. Do I need to escape these? I believe I do. There we go. That converted all of those, and let's do that one manually. Declare.not used. Shouldn't be an error in that way. We convert it to a set, but we have to take the cardinality of that set, or the amount of elements in the set, to get the numbers to match up. Save that. There we go. We could of course do some meta program trickery, or just wrap this in a function or something to get this a bit nicer, but it's gonna work fine. So now we have this dx and dy. So from 1 to 2, we have a difference of 5, 1. Let's look at the one that we have an answer for, from 5 to 9. So from 5 to 9, it's a 4, 5 difference. And we know that this is going to be 9. 4 and 5 do look suspiciously similar to a 9. And we know that we are going to have to go 1, 2, 3, 4, 5. And 1, 2, 3, 4. So we might just have to add these two together to get the difference, or to get the sum that we're looking for. Might actually be correct. 374 is indeed the number we're looking for. We can save this in our day 11 as input, give that an extension. I just like having extensions on them. You don't really need to in them. And let's combine, or on Linux, I don't need the txt, I just like having it there. So this is another feature of nym. You have let and var and blocks. So instead of having to do let and another let and another let, we can just have one let and say this is going to be a block of things that are defined as let. Same for var and const, as I'm doing up here. All of these are variables. Saves a bit of typing, makes these sections sort of a bit easier to see. Kind of coerces you into putting these sections in one place instead of spreading your variables out, for better or for worse. But of course you do miss, you can't just look at this line and know if this is a var or let. Well, in this case you can, because lets have to be initialized, and this isn't initialized, but you couldn't look at this and tell if it's a var or let without going up and looking at the context around it. If we now go ahead and say input.txt instead of a sample input, we will see that we have quite a bit of a bigger number here, but it's the right answer. 1 gold star closer to restoring snow operations. Great. Let's see. Do we have any comments here yet? No? Is there oh yeah, we do have Twitch comments. Oh, that's weird. Oh, I was in the AoC IRC room. Yeah, hi. Intersection, yes. That is the word I was looking for. So what we're using here is a set intersection. No, it's not the intersection. We're looking for the what is it called? This one, even though they are not the same sets, they should. The difference between two sets. So we're looking for. We are getting the set difference. So everything in A that is not contained in B. So our A is all the positions between the two, and the B is a set of all the galaxies. So if you look at the positions between us, remove all the galaxies, then we are left with the empty lines between us, and those count double. So right, that was quite easy, quite fast. Let's look at part 2. Part 2. The galaxies are much older and thus much farther apart than the researcher initially estimated. Now, instead of the expansion you did before, make each empty row or column 1,000,000 times larger. That is, each empty row should be replaced with 1,000,000 empty rows, and each empty column should be replaced with 1,000,000 empty columns. In the example above, if each empty row or column were merely 10 times larger, the sum of the shortest path between every pair of galaxies would be 1030. If each empty row or column were merely 100 times larger, the sum of the shortest paths between every pair of galaxies would be 8,410. However, your universe will need to expand far beyond those values. Starting with the same initial image, expand the universe according to these new rules, then find the length of the shortest path between every pair of galaxies. What is the sum of these lengths? So, our solution is, of course, very tailored to this. So you remember at the beginning where I said we could do it in the parsing step and just add in empty lines in the galaxies list? That would not work if we needed a million empty rows between each of them. But in our case, it's as simple as just timing these by a million. And of course, for nice stylistic syntactic reasons, or purely stylistic visual reasons, we'll do this. So in M you can have underscores to separate your numbers, typically used for 1000 separators, but you can use them for whatever you want. And our solution should be just about as fast as our part 1. And we can submit. Oh, that's not the right answer. Your answer is too high. Right, it should be replaced with this amount of empty rows. So we actually need, so we count them once here. Now we count them 1,000,001 times. That's obviously not what we want, so we need to do this. Now we count them. We replace them with a million empty lines. Oh. Now I have to wait for a couple of seconds. So that's the sort of anti-cheat of Advent of Code. You can't give answers too quickly. Otherwise you could have just set up something that guessed all the numbers. Well, I guess not all the numbers, but you could start guessing. Do we think 19 seconds have passed? I'm not sure. Maybe now. You don't get a penalty for going another one. Yay! That's the right answer. You're 1 gold star closer to restoring snow operations. Nice. Well, that was easy. So this is one of these days I really like, where if you have a good solution for part 1, part 2 is just some simple changes. I guess I don't think we'll start on a new day, but we can have a look at my day 8 because I have a little bit of time before I need to get going. So if you remember for day 8, we were looking at this card game. We had this card game and we started looking at these maps and doing left right to navigate the sort of lists here of nodes. And this is the kind of Advent of Code thing that I really don't like, because here you have to look at your input. You have to sort of find patterns and reason about your input. And as a computer scientist, you should never look at the input. You go by your definition of what your system is supposed to be doing, and you don't trust user input. I guess this isn't user input, so this is just optimizing for a pattern in our code. But basically our solution for day 1, or part 1, which was just go from AAA to ZZZ, following this pattern recurring, or the pattern up here recurring, which was pretty easy. This runs in, so if you do a release build of part 1, it should run in probably in some couple of milliseconds. Oops, part 1, bit of a spoiler there. So yeah, 3 milliseconds to run part 1. And basically, so all of this is just types and the parser written in npeg. Then we have a parse input that's parsing the parse input is just wrapping the parser and showing off some other stuff. So this is the only actual logic in here. We just start at the map. We go through all of the steps, choose the left or right, increase if we get to the end, break out of the loop, and tell it how many steps we took. I tried to do the dumb thing for part 2, but spoiler, as you can see, that's going to take quite a lot of iterations. So this took a couple milliseconds, 3 milliseconds. Now we're doing 6 at a time. So let's try to do so this number divided by 6, because we're doing 6 at a time, and divided by this number. It is this much slower than our solution. So at 3 milliseconds, that's the amount of milliseconds it would take. There you have seconds. Here you have minutes. And then you have hours. And then you have days. So it would take us about three and a half day of running that, which means, ironically, by now I would be closing in on a solution if I had let my computer run. But yeah, not a great way of solving a day-long puzzle. Someone, of course, shared in the chat that the solution was to find the distance you had to go from here to its said. So this would go left to this node, and then it would go right and find this. So the distance from this to this is 2. To this is 2. And the annoying thing for me was that, so yeah, that's 2. So you do this one, you do that one. Now we loop, we're back at the left here, and we're at this one, and this one matches. So here, since we have wrapped around, and it doesn't say anything that we are gonna wrap around, but we wrap around, and we find a node that just basically looks the same as the A node. So of course, running this on a node that looks exactly like the A node, we jump to the same thing, and this is a looping pattern. This one, it goes to B, it goes right to C, then it goes left to this one, and we're now at this one. Oh wait. Go left, go right, go left. So this one doesn't end at an intersection. This ends after the first one in an intersection. And then it goes right to this one. Basically, it's, yeah. My solution, basically what I ended up doing, I ended up looking at the input. So if the current location that we're at ends with a Z, so if we have found an end, I basically said, okay, echo out all the information that we know about this position. So where we are in our directions, where we started from, like what the start node looks like, what the current node looks like and the amount of steps that it took to get here. So if we now look at this, if we run part 2, we don't need this. Oh, I seem to have a hiccup. I lost connection to my IRC client here. The stream seems to be going. Maybe the Twitch chat is having some trouble. No -r. Oh. -r. Right. So here we go. We can see. Oops. We can't see. Oh. Because I say at the end of our loop, break out of the loop. So I've obviously refactored this code since I wrote it. Just don't break. So for the first one, we will see that, yeah, it just loops. It finds this A node, which goes to this one. But now on our Z, we can see that it's flipped. And in my data, all of these are flipped for some reason. Now we echoed out just steps. If I say that steps is equal to 0 in this, we will now see that it takes the same amount of steps exactly for every time it finds a end node. And the same is true if we don't start at the first one, we start at the second one. We can see that this is also, it has a fixed number of steps to go from this node to this node. And again, these are flipped, but it doesn't matter because all of these lengths are the same. And that means that we can do, because the input is shaped this way, we can do what the commenter last time said. So basically what we're doing here is if we're at an end, we add the distance, we add the steps that we took to get here into the distances, and then we calculate the least common multiple of these. So the least common multiple, least common multiple is basically the lowest number. So here you have least common multiple of 4 and 6. So multiples of 4 are 4, 8, 12, 16, so on. Multiples of 6 are 6, 12, 18, 24, so on. Common multiples, so those which are multiples both of 6 and of 4. And remember, in our sequence, this would be amount of steps before we found the first Z, amount of steps before we found the second Z, the third, the fourth, the fifth, the sixth, and same for the next starting node. So these would be each time these multiples lined up would be at 12, 24, 36, 48, 60, 72. And of course, the smallest one here is the 12. So the least common multiple is 12. That's the shortest amount of steps before they both become a Z. So applying it to this, it would take the numbers like this, and well, I'll let it run for a bit too long. So I'm not sure we're going to be able to go back all the way to the A1. Oh yeah, we were. So we would take this number and this number, and then calculate what is the least common multiple between those. And And of course, in nim, you have in the maths module, you have this least common multiple, which takes an open array, so anything which is sort of array-like, and just calculates the least common multiple of all of them, which means that for all of the repeating loops, find the least common multiple. Of course, that repeating loop part was only evident after looking at the actual input and parsing out the actual input, or looking at it, reasoning about it, and finding a pattern in the output or in the input. So yeah, my least favorite kind of advent of code thing, where you have to find patterns in the input. But hopefully, now that we know we're one bit smarter, we can think about that for the next ones, and see if we can't use this knowledge to more easily solve the other ones. Should we peek at these? I kind of want to, just for the story of it, but I guess we shouldn't. It's breaking with the theme of the stream. Yeah, as always, my solutions will be on my GitHub. On my GitHub here. Yeah, I haven't posted day 8 either. I'll post day 8 with my new solution as well, and of course, solution for day 11. And I'll get the videos into the YouTube playlist as well. But that is it for today. And hopefully, yeah, no more chats. Hopefully for tomorrow, we might have time to look at 2 days. Maybe, hopefully. Depends on how long it will take me to solve day 12. But if we're able to do day 12 as fast as we did day 11, then maybe we'll do 10 or 9 as well. Right. That was it for today. Hope you enjoyed a bit faster one this time. I mean, took an hour. By no means the fastest anyone solves these. It's crazy how fast people are able to solve these things. But yeah, that's it for today. As I said, have a good Advent, a merry Advent. Do you say that? Oh wait, I have some effects from last year. There we go. Advent of Nim. I should put this on to begin with. Yeah, Advent of Nim. Hope you enjoyed. Hopefully I see you again tomorrow.